Hello guys, welcome back to another video on my channel. Now in the last video we did an integral. We will do another one in this video, but this one involves complex analysis and special functions. So it's quite interesting, and I thought it's a long time since we've done some special functions. So let's get started. So consider I to be integral 0 to 2 pi ln absolute value gamma of e to the I theta times Riemann zeta of e to the I theta d theta. The gamma and the zeta are taking a complex argument. E to the I theta is a complex number. Now, what we're going to do is we're going to notice absolute value e to the I theta, and this will be the complex norm. In this case, the complex magnitude is 1. So, absolute value of gamma of e to the I theta equals absolute value gamma e to the I theta times e to the I theta, because e to the I theta has norm 1. What that allows us to do is we can rewrite our integral I as integral 0 to 2 pi ln absolute value gamma e to the I theta times e to the I theta times zeta e to the I theta d theta. Now use the recursive formula for the gamma function. Gamma of z times z is gamma of z plus 1. So in the integrand, we just have gamma of 1 plus e to the I theta times zeta of e to the I theta inside the natural log d theta. And what we can do is we can introduce a parameter r, and we'll have to take the limit as r goes to 1. So we'll just introduce an r up front, multiplying with the e to the I theta, because that will be the polar form of any complex number. E to the I theta on its own is the general form of any unit norm complex number with an r that represents any arbitrary complex number. But since we did not have an r here and we have one here, we have to take the limit as r goes to 1. So limit r goes to 1, integral 0 to 2 pi ln absolute value gamma 1 plus r e to the I theta times zeta of r e to the I theta d theta. Why does this help? Why did we introduce parameter r? Because this was fine, and then we introduced parameter r with the limit. This might seem like an extra step, a hurdle in our way, but we have this Gauss Mean Value Theorem, which requires the integrand to be of this polar form. So what the theorem says is, let f of z be an analytic function in the disk, the open disk in this case, as where norm z minus a is less than r, capital R, then f of z equals 1 over 2 pi integral 0 to 2 pi f of z plus r e to the I theta d theta for r but in this radius of analyticity, so 0 to r. So you notice the integrand has an r e to the I theta dependence with the d theta on the entire circle from 0 to 2 pi, which exactly matches what we have here. But before we can actually use this, let's prove it, because it's not too difficult to prove once you know Cauchy integral formula. So recall the Cauchy integral formula from complex analysis. F of z equals 1 over 2 pi I, a contour integral over contour C, f of a over a minus z dA, where f of z is analytic inside contour C, such that absolute value a minus z is less than r. That is one condition we are taking, because we had this region, this open disk here. So we're taking that open disk domain, region of analyticity, so that we get exactly what we had to prove. So then we parameterize contour C, because contour C is such that it's around the point Z. So A, which was the contour integration variable, will be parameterized as a circle centered at Z. So we have Z plus R e to the I theta, with R going from 0 to capital R. dA is then Ri e to the I theta d theta, because Z is a constant. Z is just some fixed complex number, which is well represented by the left hand side. So with this parameterization, we have f of z equals 1 over 2 pi I integral 0 to 2 pi f of z plus r e to the I theta over r e to the I theta, and the differential factor is ri e to the I theta d theta. Factors cancel out nicely. Ri cancels with one I here and r here. So does the exponential. And we're just left with 1 over 2 pi integral 0 to 2 pi f of z plus r e to the I theta d theta, where the small r is between 0 and r, exclusive. And that's it. That's what we had to show. All we did was take Cauchy integral formula over contour that was satisfying this region, that was inside this region, such that f was inside, or analytic inside it. So such a contour satisfied this condition, because we knew f of z was analytic in this open disk. We parameterized it accordingly as a circle that's centered at z, with R that was satisfying this this disk region, and we just simply get this. So that's it. That's simple proof. Now notice that in our case f of z is ln gamma of 1 plus z times Riemann zeta of z. This is analytic near z equals 0, and the z we had here on this left hand side and the right hand side is 0, because there is just, if you go up to what we had before, there is just r e to the I theta. There's no z plus. There's no z plus. This one is separate, because the function is gamma of 1 plus z times zeta of z. There's no there's nothing adding in both the arguments. There's nothing adding both of them up. So our z is just 0. The fixed complex number is just 0. The center of our contour is just 0. Z equals 0. And we just have, from the Gauss Mean Value Theorem, this integral, limit r goes to 0 to 2 pi f of z plus r e to the I theta d theta. I'm writing z just for the sake of generality, equals, by the Gauss Mean Value Theorem, limit r goes to 1, integral 0 to 2 pi f of r e to the I theta d theta. And now we just substitute this this left hand side here. So that gives us 2 pi limit r goes to 1 f of 0, because z was 0. Now we know what f is. We just plug in z equals 0 there. So we have 2 pi times ln absolute value gamma of 1 plus 0 times zeta of 0. Now this becomes 2 pi ln absolute value gamma 1 times zeta 0. Gamma 1 is 0 factorial, so that's 1. So we have 2 pi ln absolute value zeta of 0. Now, by the Ramanujan summation, or we call it the zeta regularization, we know the value of zeta of 0. It's minus 1/2. So using that, we have I equals 2 pi ln absolute value minus 1/2, which is 2 pi ln of 1/2, which is minus 2 pi ln 2. from the properties of the log. And that's it. That's the final answer. Now I skipped some details actually. I had to show that f of z is actually analytic in a neighborhood of 0, because you go any further, you go between in the range of 0 to 1. Real part of z is in, if 0 real part of z is between 0 and 1, the the zeta function is said to have its poles there. And the gamma function, well, it has its poles on the negative integers. So we actually are really working in this tight neighborhood around z. And so capital R would just be some small, arbitrarily small parameter in this case. And that's fine, because the Cauchy integral formula totally holds for such tight neighborhoods around some points. Like in this case, z equals 0. And that should more or less be it for this video. Please let me know what you want to do in the next one. If you have any suggestions, please email me. Otherwise, I'm thinking of starting a linear algebra series. I'm going to follow Sheldon Axler's textbook. I think that will really help many people. So stay tuned and peace out.